So sometimes in civil engineering, we'll have forces that act like this, kind of like a force field, a distribution of forces. Like imagine I had a column here. Imagine the wind on this column. The wind at the bottom will be small, but as we get up higher and higher, that wind force on our column will be bigger. So, let's work through how we're supposed to deal with these sorts of forces that act like this. We call these distributed loadings. So notice first that we have this. So W here is sometimes known as the load intensity. And interestingly enough, the units for it are going to be force over distance, newtons over meters, pounds over feet. So for this equation here, if I were to say plug in 3, x is equal to 3 into this equation, I would get that the load intensity here is 67.5. And again, that's in newtons per meter. And that's what I get if I plug in 3 into this equation. For instance, if I was to take that 67.5 and times it by, who knows, some distance, maybe times it by 0.5 meters. Remember the units here, newtons over meters times meters. My meters cancel out, and what I'm left with is newtons. So I would get 33.75 newtons. So that means from that 3 going out half a meter, I have in total 33.75 newtons of force from all of this distributed loading right here. 33.75. But I got to be very, very careful with how I think about this. This logic isn't quite correct. Because we can agree, as we go from 3 to 3.1 to 3.2, etc., my W actually changes its value. We can see here that it's getting bigger than that 67.5. So some of our purple distances, or purple points here, are at a higher W than 67.5. So this 33.75 is actually an underestimation of all of the force here. So here's how we have to think about this. The smaller I make this number right here, the more accurate my prediction will be. Because if I make that smaller, I can see that my W changes less. And if you think about it, the smallest I can make this thing is dx. As small as you can think, 0.00001. You know, just very small. It's the calculus idea of a differential. So if I take this dx here and multiply it by my loading intensity, what I'll get is the tiny amount of force at that location. So if I do my W here, multiply it by that little bit of dx, I'm going to get the little bit of force acting at that x from that distributed loading W. And again, if you're wondering why is it df, remember dx is very, very small. Imagine not putting 0.5 in here, imagine putting 0.00001 in there. If you multiply it by 67.5, you'll get a tiny amount of force acting at this x. So I can do dx times my W here to get my tiny bit of force here, and so on and so forth. So really what I want to do is I want to add up all of these tiny forces using the calculus integral to get the total downwards force from this entire distributed load. In this case, our W is 2.5x cubed dx. We want to add up all of these little forces for all of my dx locations, and we want to start adding up right here basically at x is equal to 0. So x initial will equal 0, and we'll keep adding until here at x is equal to 4. So that is my x final. And this will allow me to calculate the total force from this distributed loading. So now let's just let the math run. We'll get 160 newtons. Obviously the direction is going downwards. So we know that in total, this entire distributed loading represents a total downwards force of 160 newtons. Now our next question is, what moment arm, what distance should we place this force away from our endpoint such that it creates the same moment as our distributed loading? It really goes back to the idea of equivalency in engineering. This force needs to behave the exact same way as this whole thing. It needs to create the same total downwards force, got that, and it needs to create the same exact moment as well. So for example, let's just say we went through the math and got that this total distributed loading here creates 560 Newton meter moment about our point A here. We would be able to solve for the placement of this total downwards force here. So let's do this. How do we actually calculate the moment of this entire distributed loading about this point? So moment of a force is equal to that force times its lever arm. This is our nice simple 2D moment equation here. And to calculate one of the forces of our distributed load, remember we did dx multiplied by the W at that x, and that got us the little bit of force at that x. So really we just need to multiply this force here by the lever arm. And what is the lever arm? Well, the lever arm for this force in particular is going to be just this distance right here. And notice that this distance is the x-coordinate of this point. So all we really have to do is multiply this by x. And now this whole equation represents the tiny moment produced by this tiny force. And of course, to find the total moment, I want to use that calculus integral to add up all of these little moments, starting from 0 and ending at the end of that beam, which is at an x-coordinate of 4. Alright, so let me just fill in our number here, or our equation for the load intensity. Now we just got to do the math. So here's us taking the antiderivative, and we'll get 512 Newton meters. So that is the total moment that this complete distributed loading creates about that point A. Of course, we just have to ask the question, what distance d do I need to move that 160-pound force, or Newton force, so that it creates this same 512 Newton meter moment? And we'll do that math, and we'll solve it as 3.2 meters. So this distance here is 3.2. So I fully reduced the distributed loading to one force, which has the same force as the complete distributed loading, and it creates the same moment as the distributed loading. Alright, hope this concept made sense. Feel free to ask any questions you may have in the comments.